Now let's turn to the property of resistance and its behavior in AC circuits instead. The simplest AC resistive circuit is shown here on the board. It's an AC source. Again, it's the circular source with the little squiggly line in the middle indicating an AC voltage, and it's just connected up directly to the resistor. The time domain voltage source, E sub t, is going to drop all of its voltage across the resistor. There's only two elements that are in parallel. All the voltage produced by this voltage source is going to be dropped across this resistor. And therefore, ET, the voltage source, is equal to the voltage drop across the resistor, in this case indicated by ER. Right? Additionally, since there's only one loop, Kirchhoff's current law tells us the current being sourced from the voltage source must all flow through the resistor. So the current here, I, coming out of this voltage source being sourced by the voltage source, has to be equal to the current flowing through the resistor. So we know that because they're in parallel, the voltage across the resistor and the voltage of the source are the same. And because there's only one loop, the currents have to be the same. So what we can do is we can use this model to rewrite the Ohm's law for AC circuits. And we'll rewrite that as the resistance is equal to the voltage as a function of time divided by the current as a function of time. In this notation, the lowercase letters for voltage and current are being used to indicate AC quantities, and the lowercase t within the parentheses indicates that the voltage and current are both functions of time. More specifically, if we wanted to write this Ohm's law equation, and I'm just going to make a little bit of space here, we would have to say that the voltage is a function of time. Remember, using a sinusoidal function, we've got the max or the peak voltage times the cosine of omega t plus phi sub v and that's going to be equal to the resistance times the max voltage cosine of omega t plus phi sub I. So here I've just rewritten that same equation again. So V of t equals V max cosine of omega t plus phi sub v, and that is equal to R times I max cosine of omega t plus phi sub I. So that is technically Ohm's law written for an AC situation. You'll notice that in this equation, R here was not written as R of t. This is because the resistance value is constant and doesn't change with time, and R of t is therefore unnecessary. You should also notice that according to the above equation, V of t and I of t will have the same frequency, right? Omega t is matched here. That's the same omega t. So the frequency of the resultant current flowing through the device has to be equal to the frequency of the voltage source applied to it. For resistive devices, we'll find that phi sub v and phi sub I have to be the same. So you'll see that the phase is also the same. What this tells us is that since frequency is the same and phase is the same, resistance has no effect whatsoever on the timing of the AC waveform, only on its magnitude. What this is really saying is that at the terminals of a resistor, there is no phase shift between the current and the voltage in AC quantities. So this image depicts this relationship where the phase angle of the voltage and the current are equal. The signals are said to be in phase because they both reach the corresponding values on the respective curves at the same time. For example, they are at their positive maximum at the same instant in time here. Right? we see that the voltage and the current for this plot of a resistor, this is the voltage and current through a resistor, as they go through the AC cycle, these are directly in phase. So what that is saying is phi sub V and phi sub I for a resistive device has to be 0, or have to be equal, or phi V minus phi I equals 0. All we're saying here is that they're the same. Graphically, we can easily see that by just looking at the voltage waveform, this big solid line here, versus the current waveform, the dotted line, and we see they reach their peaks at the same time, they reach their zero crossings at the same time, they reach their negative peaks at the same time. Mathematically, we say that they are in phase. A second method of representing this relationship is by plotting the voltage current as the voltage and current as vector quantities. So we're going to take the voltage as the reference quantity. Here we plotted it in the positive x direction. We showed that the current and voltage are in phase because the voltage, the arrows point in the same direction. I've got this blue line representing the voltage, E sub t, and the current, which is equal to E sub r, remember. And then the current flowing through the circuit is in phase. 0 degree phase shift between the two is what we're indicating there. If there had been phase shift, we would see that this vector would rotate either in the positive direction or in the negative direction. But for purely resistive circuits, whenever there is just an R, there is no phase shift between the voltage and the current, meaning the timing of the waveform has not been affected. And that really is the essence of the property of resistance, is that it affects only the magnitude of the result. It does not affect any sort of timing relationship.